All right. So we had the chapter on the introduction, where we basically posed the challenge of computational materials designs as a minimization problem in chemical compound space. So in all your nuclear charges, all your spatial degrees of freedom, and the number of electrons, right? So from a QM perspective, that's the space we have to sample. And you have, maybe write it like this. You have a set of atoms, right? So this is 4n dimensions, n being the number of atoms. And so your R is vectorial. And strictly speaking, you should also include spin variables, right? So you could have different spin states, right? So this would then mean that we would have the number of electrons times the possible number of spin states, right? So this is, but usually we don't, we limit ourselves to electronic ground state properties. So in this variable space, right, this is the space of our inputs. We have then a property which we want to optimize, right? And we do that by minimizing its deviation from the target, right? So this is the instantaneous one. So let's say this is our entire chemical space is the sigma, right? So this is the sigma. And this is, maybe there's more than one property we want, right? So you could have something like this, where you sum over those. You want this to be convex, so we squared. And we want to include them all. Now, one property might have different units or might have different importance than another. So you would also like to have some weight for each property. So this is the problem in general, right, which we have to solve. And we discussed cases where this problem is easy. And also in this introduction, right? Then we proceeded to the quantum mechanics, which basically allows us to go from some input to some property, okay? So strictly speaking, we should put quantum mechanics as well as statistical mechanics, right? So this is the forward map, right? And we discussed some of the well-established details on this of varying levels of sophistication, and also, of course, not in a comprehensive manner. Clearly, you can spend multiple courses just on these forward maps, right? So this is not something we will be able to manage to deal with comprehensively in a single chapter of this course. But we have identified this as crucial for solving the problem as we posted here. And the reason is that we want to tackle in general, you can solve this problem iteratively. So solving many times the forward problem is a possibility. And so these QM methods allow us to do this in general. That means we can deal with any property, right? And any chemistry, any chemical class of compounds. At least in principle, right? So that's the immense power that is encoded by the laws of physics, which, of course, we want and maybe we even need to exploit. So we finished this chapter, and now so this is basically what defines our property and what defines our forward map. And I'd like to talk now in the third chapter about chemical compound space, which means we want to talk about the sigma. So there are, of course, things are also intertwined, and it's not always obvious how to separate these two, but there are certain aspects to sigma that go beyond just the periodic table, and so we should talk about that. So we discussed last week already, basically, that there are three scales that typically occur in chemical compound space. And what I'm referring to now is a chemical compound being defined. So a compound is defined as a system where a certain stoichiometry, so this is a certain stoichiometry, that means the set of nuclear charges, really, is fixed, and for which so it's a certain stoichiometry and charge. So Q, and Q is the number of protons, the difference between number of protons in your system. So number of protons is the sum over all nuclear charges minus number of electrons, right? So a certain set of nuclei, a certain charge Q, and a certain electronic configuration, right? A certain electronic state. As you know, Schrödinger's equation gives you an entire spectrum of solutions, right? And so you have to specify which solution you're talking about, right? And on that solution, we have the potential energy hypersurface that is being spanned by all the spatial degrees of freedom. So we have a certain stoichiometry, charge, and electronic state for which the atomic positions are in or close to, remember these can be Studmak averages, local, can be also the global, but most often usually you have much more local than global minimum surrounded I should say potential energy surface minimum, right? PES, surrounded by areas sufficiently high such that for the conditions considered the lifetime does not vanish. All right. Okay. It's sort of a, it fits on one page. So this is a definition which is fully consistent with our first principles view on matter and with what an experimental chemist or material scientist is typically referring to when talking about a compound. Yeah. Now there are certain exceptions. For instance, if you have oscillations between one minimum and another, right? This can occur at ambient conditions. And so you have these oscillatory reactions, for instance, but these are really rare events, right? Typically, the free energy surface is shaped in such a way that your system will be in one free energy minimum then. So let me maybe rectify this. This should really be the free energy surface and not the potential energy surface. So this should be an F and not a P, right? But you do have situations, right, where you have an equilibrium going from one potential energy surface to another, but then the free energy will be in a minimum, right? So that's even more precise if you use the free energy surface. So this is just a compound, right? Remember that in quantum mechanics is larger than that, right? It also includes the description for barriers, for saddle points, right? For excitations, changing from one surface to another. Right? All these things are still part of quantum mechanics, right? So chemical compound space, as defined here, is a subset of what is actually possible in terms of Hilbert spaces, which we can use to cope with chemistry at large. All right. So this means we have typically we can distinguish, right? From this follows that causally speaking, there are roughly 3 scales, right? Scale number 1 is the composition. So that's the stoichiometry, right? Scale number 2 is what is known as constitution. That is typically the bonding network, the graphs, right? And scale number 3 is conformation. So this is angles and torsions. And also, quite importantly, if you wish, but we could define a, either you call it, yeah, maybe let's include it here. We could also say non-covalent interactions, so van der Waals interactions. So this is a rough categorization, right? In terms of energy scales, they can be overlapping, but roughly speaking, the energy scales differ largely, right? So when you change composition, right, you're often changing things like one hydrogen atom, right, is worth half a hartree. Right? That is roughly 300 kcal per mole, right? So just as an order of magnitude, right? One hydrogen atom is roughly 300 kcal per mole. Now, if you, right? Let's go to 1. So we know the atom of an energy roughly scales as -1/2 Z to the 7/3, right? Nuclear charge of that atom. So it's more than quadratic, right? So this means let's say a carbon atom, right, would be something like yeah, more than 36. So half of that is 18 hartree, right? And that times 600. So you're talking 1,200, nearly 1,000 kcal per mole, right? Just for the carbon atom. So you should develop a kind of intuition here, right? Now, what is a constitution word, right? It's about breaking bonds, covalent bonds, right? So a covalent bond is order of magnitude as 100 kcal per mole. Right? That's roughly a covalent bond. And so conformation, so changes in the torsion, right? The angles, intermolecular interactions, we are talking roughly on the order of 10 kcal per mole. Can be less, like 2, right? It can be more, like 20. It depends on the system you're talking about, right? Same for bonds, of course. If you go single, double, triple bonds, depending also on the bonding partners and so on. So you'll be generous in the variance in these guesstimates, right? But on the scale of your energies, right? That's roughly what you should be looking for. Now, we talked about the partitioning problem of your stoichiometry. Now, where does this come from, right? We basically go back and we start out with the elementary particles, right? So we start out with electrons and protons, right? So starting with Ne electrons, right? And Np typically similar to number of electrons, because if the charge is too large, you will have unstable systems, right? And Np protons, one can ask how many stoichiometries can be realized. Now, this is a partitioning problem, right? Integer partitioning problem. And I don't know if it was the first, but maybe the last time this was discussed in the literature was by your very own professor. So you can look into the paper where I discussed this. I'm not. I think I'm the first to discuss it this way, but it's such a basic thing. I wouldn't be surprised if somebody else discussed it already before me. Of course, I did my literature research, but you never know if you could be in some other language or other community. So this was in the International Journal of Quantum Chemistry in 2013. So this is a problem. So the example could be, let's say, 4 protons. Then you can have all protons in one nucleus. That would then be beryllium. Or you can have 3 protons, so there will be lithium and 1. Or you can have the helium dimer. Or you can have helium and 2 hydrogens, or you can have 4 hydrogens. So I believe I didn't miss any. So these are the 5 stoichiometries you could realize with 4 protons. And in fact, these graphs are, if you make such graphs, you can also find them as Young-Ferrer diagrams. Okay. So mathematically, this is nothing new, right? It's just that this has immediate meaning for this highest compositional level in which we discuss chemical compounds. And you can show that the number of partitions I take the log of this and I plot it as a function of number of protons, right? You will see, and that figure is also, I discussed this in this paper, you will see that you rapidly reach some exponential growth. So for example, for 40 protons, you would find something like 37,000 possible stoichiometries. Now 40 protons is not large, right? That's 4 water molecules, right? So that's nothing crazy. And in terms of possibility, you see here how on this large energy scale already unfolds a huge variety, right? A huge room of possibilities. But it's still finite, right? It's very finite. But there's many, but not more than that. So it's not few, but not infinite either, right? So I think it's very natural then to conclude there will be bounds in chemical compound space, right? Where no matter what you do in this universe, you cannot go beyond. All right. So you know, if in this axis, right? You record here the number of atoms in the system. And if you go to the case where you have just one atom, then of course this is the periodic table. So the one atom case unfolds to the periodic table as you increase your number of protons, that is the nuclear charge in your term, right? So on these 3 scales, right, you can view the composition here. This is sort of the one body physics, right? So this is the physics. I mean, there can be multiple one body terms, but it's about this one body thing. And then here you have the the strongest two body effects, right? And then here you have 3 and many body, right? The angles between 3 atoms, right? There's a 3 body effect, right? Torsion is a 4 body effect, right? So you have inherent in these scales, you have this kind of hierarchy on these scales, right? So there are roughly 3 hierarchical scales, right? Right. Now, in the one body physics, right, you can focus yourself on the one atom, on the one particle case, and that is the periodic table. It goes only up to 118 or so. People estimate that there could be, for much larger nuclear charges, there could be stable atoms again, very large atoms. Just think about what I said earlier, right? 40 protons. That's the zirconium atom. If the same number of electrons in 4 water molecules, okay? You go to 100, nuclear charge 100, that's one atom, the same number of electrons live in 10 water molecules, right? That's nearly a droplet, right? you push all of that into a single atom. So this tells you also something a lot intuitively about the variance you should expect, right? This should be incredibly rich physics you can get from going from one limit to the other, right? Of course, you could also compare this to 100, so 50 hydrogen molecules, right? So this is sort of what the periodic table then represents in this view, right? It's the simplest possible stoichiometry on the coarsest level and scale on the highest level and scale of things. And the different representations of the periodic table, I really like the one of a spiral where you go like this, right? So you start out with this width would be for the S elements, and then you have the P elements, right? And then you would have the D elements, and the F and so on and so forth, right? This encodes. So this would be your principal quantum number N, right? And this would be your angular momentum quantum numbers M. And the progress on the spiral is your nuclear charge, right? So this is your Z. Now, we mentioned before in the examples of simple chemistries that you can rearrange this differently, right? The natural order of your nuclear charge, right, in terms of counting this as integers in increasing order. This is very intuitive, but not necessarily the best ordering system, right? And so the Petit-4, so you can change the order of elements from some monotonic map to the nuclear charge to really to any other order that better fits your need. In particular, as you know, for instance, the ionization potential as a function of the Z also reflects the periodicity. Looks something like this. No, it should be. Right, so you have this this kind of periodic behavior where within, let's say, within a given column, you might then observe smooth behavior along the column. So that's very much where the periodic idea comes from, and that's what triggered, of course, Mendeleev to postulate the periodic table, right? Now, Pettiford proposed different numbering scheme. So he basically reshuffled the arrangement, right? He took away the nuclear charge as an index and reshuffled things such that important properties become linear, right? So to turn important properties not only monotonic but actually linear, it's quite remarkable. I don't understand this, right? Why would it be so linear? But in composition, right? So, for example, and I think I showed this also in the introduction, you look at the formation energy as a function of the Pettiford number, then you will find something like this for FCC. This would be the nitrides. This would be carbides. And the ordering would be something like zirconium, tungsten, chrome, technetium, mangan. So this is not the periodic table ordering. All right. So you will find this in Pettiford's work, but this tells you something very interesting, right? It tells you that your observables, if you have an observable which depends on the nuclear charge of one atom, you have only one atom, right? It's the only thing you vary. Same crystal, same bonding partners, you only vary one atom. And then by performing a transformation, a simple reordering of your nuclear charge, you can turn this property linear, right? So this can be a very complicated property. You can turn this property into something. So this is say complicated. This is now linear into some transformation, some trivial transformation, reordering of your Z. Right? And so it's not clear how to systematically and generally obtain these reorderings, right? So Pettiford, through extensive experience and testing and elaboration, figured this out, but only for the simplest, the one body, 1D case, right? Now, there's no reason to believe that this should not be possible for more bodies, for more variables. But this is, if you wish, where the field is at the moment. Right? So, in some sense, it's very sobering. Right? Our understanding of compound space and our influence, where we can control it and make our life easy, is at the moment still at the one body level. So, so not clear how to find transform in general. Please.
I think I don't quite get it. So because it seems simple, but if I take, for example, a different property, let's take the easiest one, just like the energy of just like a single atom, which you've like shown is roughly kind of minus z to the minus 7 over 3 or so. So roughly minus z squared. For that property, it will never be possible to find a reordering where it's linear, just because the function fundamentally is not linear. It's already properly ordered, but it's not linear. So you would have kind of lost at that point, right? I mean, you would assume that for most properties, this will not be linear after reordering. And maybe there's some lucky shots where it is linear, but why should it be?
Why, if you take a logarithm, you would have 7/3 of the logarithm of z.
Which is also not linear, which would be then logarithmically in z, right?
Sure, yeah, will be linear in the logarithm of z.
But if you allow arbitrary transformations of z,
yes,
then it's kind of trivial to linearize, because then, I mean, what you could always do, you could just like calculate the property and just say, well, I map z to that property, that is my function, and then, well, it's trivially linearly because kind of your ordering is already the result. So
right, for any 1D case like this, you can do this, but the amazing thing is that for here, what you see on the right here, it's the same ordering for nitrates as for carbides and other materials, right? So then if you're ordering, if this ordering you obtain, right, if this is more general than just this one case, this one property, this one case of materials, then you found something very valuable. But I agree with you, if you just have this one case, then it's trivial.
And I mean, if Pettifor's ordering was so great, then we could just try it out for different properties. And I'm sure he has done that. And probably everything he hasn't published are probably things where it hasn't worked out.
Yeah.
And if you took a different ordering, well, then for his example, it wouldn't work anymore, right? So
that's right. Then it gets worse. So it's also, the universality, right, is limited, right? So this is the question, right? Is there a map that would be universally, even if it's just this 1D classes of chemistries, right? I don't think there's yet a universal class which then works for all chemistries and all possible properties, right? So let me just give you, I have here a paper from Glave, so more recent. So Pettifor was in the 80s, right? More recent work includes Glave, Sana, Hardy Gross, and Michael Marquez, who published a modified Pettifor scale in the New Journal of Physics in 2016. Okay. So this is active, yes, and it's amazing how simple and basic it is, right? And for example, to the best of my knowledge, we have not yet been exploited exploiting such simple transformations in order to reorganize our data for improved machine learning, which obviously we should do. So, okay, but that is advancing too fast. I wanted to now briefly come back to the question, the second scale, right? So we have, if you wish, you provide some number of protons and some number of electrons, and then you get many different possible stoichiometries, right? So this is our first scale, right? These are different sets of these. And then, and they differ by hundreds, if not thousands of kcal per mole. And then for any of these, right, you could consider, so these are the compositional isomers, if you wish. And for any of these, you can define graphs, right? And these are the constitutional isomers, right? So they share all the same stoichiometry, right? So these compositional isomers, they vary in your stoichiometry. So the constitutional isomers have fixed stoichiometry, different graphs. So this is on the order here, let's say 1,000. This is on the order of 100 kcal per mole. And then for any constitutional isomer, and this is, so the number of graphs, right, is known to grow combinatorially. Number grows combinatorially with number of vertices, which is number of atoms. And for any such molecular graph, you can then consider all the conformational isomers. And these are immensely important. They just think about the tertiary structure of peptides and proteins. So this is how they differ. Right? They have the same. Typically, these peptides are the same constitutional isomers, but they function or they don't function depending on their conformation. And there's even something known as Leventhal's paradox, right? Which states that there are so many possible conformal minima. If in the age of the universe, any given protein could not sample them all. So it's a miracle that we actually get our folded protein, which functions, right? So people have worked on this. You can actually show there's some funneling mechanisms, so we actually don't have to sample all of them. So that explains that, but still the mathematical number of minima is so gigantic, right? So it grows also exponentially with number of atoms, that you have this immense growth at every one of these three levels, right? So this is the first level, the second, and the third, right? So yeah, so this is basically just in terms of compounds, not talking yet about reactions, about electronic excitations. This is what we can deal with just using quantum mechanics, right? So this is the immense power of quantum mechanics and statistical mechanics. And if you now have a better grasp, right? So you shouldn't be surprised because of this discussion that, for instance, and I mentioned this slide in our first introductory lecture in 2004 and in 2017, there were some Nature, in the journal Nature, there were some, in 2004 there was an entire issue, and in 2017 it was a comment on chemical space. Contributions in Nature on chemical space. Now, a chemist typically or often refers to a compound by ignoring the third level, right? So they only talk about a given molecular graph, and they presume that the conformational degrees of freedom are either irrelevant or are being averaged out, which in some cases is a valid assumption. In some cases, it's clearly not. So you have to be careful when talking to experimentalists who not necessarily have such a clear and rigorous definition of compound space. Okay. So in these contributions, for instance, the number of medium-sized, right? So that means few or rather small number of atoms, right? Stable, so that means there's a molecular graph, organic molecules, so that means heavy in carbon content, right? Proportionally, there's a lot of carbon. Typically, more than 50% of the heavy atoms should be carbon. This number is guesstimated to be 10 to the 60. Okay. So this guesstimate, right, corresponds basically to a small subset of stoichiometries and their graphs, right? This would be 10 to the 60, right? And all the other stoichiometries, all the conformers, all the other graphs of other stoichiometries have been ignored when putting out this number. Now 10 to the 60 is larger than we have atoms in our solar system. So that's a crazy number, right? So, but again, I'd like to stress it's not infinite. Right? So again, there will be bounds on what we can do in compound space, even though it's so large. All right, so with this, I'm sort of done with the introduction to the chapter on chemical compound space. I'd suggest we take a little break and we reconvene at 9:15. Okay, let's continue with the lecture. So before we conclude this part of the course, I'd like to still highlight one thing. You could view, and this is quite important, you could view this as level 0, right? So the number of electrons, right, is of course an obvious concern, and it implies also which kind of state are you talking about, with which electronic configuration. But in principle, you know, as you can see, the size of compound space unfolds from the levels below, right? So the number of electrons is really a very low dimensional finite quantity, which is not responsible for the immense size of chemical compound space. So if suppose we had a good understanding and a good framework for each electron number, right, that would already be immensely helpful. Varying number of electrons is really not our primary concern as we navigate chemical compound space. So in that respect, right, the kind of questions we ask and the relationships that are of our concern are not necessarily equally or similarly represented by traditional experimental sciences, right? So varying number of electrons, more specifically, is of course part of all redox processes, and there are many experiments that have been and are being made, and so this is not an infrequent concern. What happens as you vary number of electrons, but in terms of dimensionality for our chemical compound space, it's not irrelevant, but it's a minor concern, right? Okay, so we do have now set the stage for looking a little bit closer in what we can do in terms of sampling the space, right? And I'd like to describe a picture now, which is sort of which opens the way for this chapter, where we sort of want to generalize our picture of external potentials. So if you assume a certain scaffold, right? So for example, imagine you have a some polymer, and this can be really you know, any sort of polymer, but here you could have a functional group, and this could be a functional group, some functional group J. This could be a functional group I, and suppose there's a polymer. So we suppose that this is maybe a sort of repeating unit, right? So it doesn't have to be a finite system. It can also be in the condensed phase, right? So then you could easily imagine, right, that we have basically here the number of sides, right, is 2. We have two sides where we can change the functional groups, right? And you could, for instance, imagine, so this is drawn in the typical chemical way, so something like this corresponds to this, right? So we keep the hydrogens implicit. You saturate the valencies. So you could imagine your functional groups to come from a library of permissible functional groups, right? So functional group could be some element from, for instance, a methyl group, NH2 group, OH group, fluorine. Of course, you can extend this, right, also to other periods. So silane, phosphane, phosphyl, sulfur, chlorine. But you could also have a hydrogen, right? So there's a library of NF equals 9 groups, right? So that could be an affected alphabet from which we draw. And so then the particular compound space then neglecting symmetry, right, would be the number of functional groups so this chemical compound space then scales as number of functional groups to the power of sides, right? So in this case, we'd have 9 to the 2, it's 81. Possible groups. And, so neglecting symmetry. So you could imagine then this is basically a 2D space, right? So imagine some property. And this is the functional group at side J. And this is the functional group at side I. Right? And now suppose it is symmetric, right? So then we only care about half that matrix, and you could record them for any combination here property. So this will be in some units. I hope that makes sense. And so in this case, we'd have only half as many possible compounds. So the question then is, if the space scales like this, right? Naive enumeration would scale like that, right? Now, if you use that to find your best possible candidate, right? That would be the cost for complete enumeration. But you could do other things, right? So you could, for instance, say you do something more inspired by a genetic algorithm, where you fix one side and you go through all NS sides of the all NF groups of the other side, right? And then you do that for the other side, and so then your cost is something like NS times NF, and then you do this repeatedly until you find the best. So that would be the number of iterations you need. So that would be the cost for something. It's not really genetic. It's some first best search kind of algorithm, right? First best search. Now, what you could also imagine, of course, is something where you say, well, suppose I'm on this compound here. Could I estimate somehow changes to my property as I go somewhere else, right? So that would be this idea of a gradient, right? Of some what would be a derivative, right? And so if you had such a derivative, right, and that is somehow accurate, right, then you might be able to break down the scaling much more, right? So then a scan of possible derivatives might get you there. And so there's this question, right? How do you go? What is your change in property as you change, as you go in through your compound space, right? So how does your property depend on this? Is this, can we make this smooth, right? Is this something we can do actually, or do we have a problem? So we talked about the arbitrariness of the nuclear charges, right? And that we can rearrange things, right? And so we can ask the question, right? If we interpolate our Hamiltonian in some parameter, where I go from some initial system to some final system as my coupling parameter lambda goes from 0 to 1. And it does not necessarily have to be a linear interpolation. It could also be nonlinear. It also doesn't have to be global. Here I'm interpolating. This is a global, so spatially not resolved. And remember, your Hamiltonian contains the external potential, which acts everywhere where your nuclei are, right? So it's spatially inhomogeneous, and so to interpolate things globally is quite a statement, right? in some sense, it's very brutal, right? So spatially not resolved and linear, right? That's basically as bad as it gets, right? So, now, but if you have that, right, then you can ask this question, right? What is my expectation value of some operator as I change my lambda? And so we discussed the Hellman-Feynman theorem, right? So for the energy, for instance, we could use that. You could ask this question, right? I can basically go from any initial compound to any final compound, right? And I can ask this question for some initial compound, changing just one functional group, right? So, excuse me, I could say for site J, right? And then you go, suppose site J currently has the methyl group, then you can ask method to methyl, method to ammonia, method to OH, and so on until hydrogen, right? And so that diagonal element, so of course going to yourself, so the change of in your property to go to yourself, this should be 0, right? And then here you would have this derivative. Suppose it's the energy, right? So it's the energy, the derivative getting you to ammonia, starting at so evaluated at lambda equals 0. So that means at the method, right? So this lambda and here you'd had the derivative going to hydroxy at methyl and so on. Here becoming the hydrogen at the methyl. And then you can do the same thing starting out with the ammonia group, right? And then now you're changing ammonia into methyl, right? Now, is this a symmetric matrix? No, not necessarily, right? Why should the derivative at ammonia be the same as the derivative at methyl? There's no reason for you to assume such a symmetry, right? But the diagonal terms, you would like them to be 0, of course. But you basically have this matrix in compound space where you have starting compounds, target compounds, right? All right. So this is now a way how you can think about compound space, right? You go from any compound to any other. And this kind of generalization is something within the picture using the Hellman-Feynman theorem, something which I've put forth in a paper in the Journal of Chemical Physics in 2009. So in particular, you can go from any other compound from any to any other compound by calculating the Hellman-Feynman derivative at lambda with the difference in the external potential. So this is so strictly speaking, for isoelectronic changes, for same number of electrons and for the same electronic state. And this is then the difference in the final, the initial, right? Hamiltonian, which is the derivative of the Hamiltonian, if and only if the Hamiltonian is linear in lambda, as we just said. So in this way, you can go from any compound to any other compound. Now this is important, right? We go beyond this idea that we have a vicinity in nuclear charge space, right? That your nearest neighbor to carbon is nitrogen or boron, right? We don't care. Could be, right, that the derivative will be smallest there, but it could also be that it's smallest as you go from carbon to silicon or to phosphorus, right? So this is a generalization, if you wish, which would fit with this idea of a scaffold and thinking of compound space in terms of compound pairs, right? Now, also this is then is related to the question of similarity measures, which we use in machine learning, right? So in some sense, you have here explicitly encoded in the difference in external potentials, you have a measure of similarity between two different systems. Now, this expression is represents the derivative of any such interpolation, right? And you can think of, and in that paper that is being done, so in this paper, in particular, I looked at HOMO eigenvalues. Now the HOMO eigenvalue is and we discussed this before in the context of Janak's theorem, is something like an energy difference, a total energy difference in your number of electrons. And so this difference, or this Hellman-Feynman theorem, this derivative, it's a linear operator, right? And that carries through for any differences like this. So you can see in that paper, for lambda going from 0 to 1, right? The examples where you can see how this shape really looks like, right? For such a property. For example, in terms of HOMO eigenvalue, the molecule HF has a HOMO eigenvalue. That is, suppose it's here. Then you have the HOMO eigenvalue of CH4, then of H2O, then of NH3. That's how they look like. And now you can look at how these eigenvalues look like if you linearly interpolate these compounds. And for HF to CH4, you see something like this. The homo eigenvalue. So it immediately becomes obvious, right? The first order derivative should not necessarily be the same here. There's no reason for you to assume that. You also see something which is a bit disappointing. Right? If you evaluate your derivative on HF, right, then the qualitative trend is right? The sign of the slope points in the right direction. But if you do this on methane, right, the qualitative trend of your first order derivative is wrong. It gives you the wrong sign. So this points to the non-linearities, of course, of quantum mechanics, right? And it also would suggest that things are not always as easy as one would like to, one would hope to. Right? So it's good and bad news at the same time. So the good news is the problem is not trivial. The bad news is we might have to, there's more work for us. Right? If you go from HF to water, this is how the HOMO looks like. Much smoother, much kinder. Here the first order slopes, the first order derivatives would be qualitatively right. Also, if you go from HF to ammonia. Now, if you go from methane to water, you have again a problem. Let's just start from water. If you go from water to ammonia, the problem is gone. And if you go from ammonia to methane, the problem is gone too. Let me draw this. So this is roughly how the epsilon, the HOMO eigenvalue, looks like in this little matrix space of this isoelectronic series of methane, ammonia, water, and HF. There's a question?
Yeah, all the points in between, kind of with non-integer lambda, do they correspond then to kind of fictional molecules with fractional charges that kind of, where kind of one fades out and the other fades in? Okay.
So it's just a linear interpolation of these external potentials, right? Mm-hmm. And the total number of protons, right, still adds up to 10, right? And so you basically have non-fractional nuclear charges sitting there, but there's no convergence problems when you. So these were DFT numbers, so you can look up the details in this paper. So these are approximated HOMO eigenvalues, but the entire numerics is completely unproblematic.
Interesting.
All right. So this gives you an idea, right, how we can explore this space, right? The good news also is that when you look at functions like this, they look quite smooth, right? So that's not an obvious thing, right? If you superimpose, now of course these functions also depend on how you orient the relative external potentials, right? And so that's described in this paper. They are oriented in such a way that the central atom, for instance, is always at the same position, but you can see that that while the shape of these curves depends on the specific form of your delta V, for something intuitive, it looks very smooth. So these were, as far as I know, the first numerical illustrations of such continuous interpolations. In that paper, the grid, which was spanned here, occurred in steps of 0.1. The idea, though, to interpolate nuclear charges, right? To interpolate, which imply interpolations in chemical composition. This idea was proposed already much earlier, right? So varying Z, which implies that so we are talking now nuclear charge, so you go right or left in the periodic table, right? You don't directly jump one element or jump one period. So varying Z was discussed much earlier. For example, Erich Hückel already discussed the effect of substituting in benzene, as it was described by Hückel theory, right? You get the MO diagrams of your pi electrons, the effect of changing benzene to pyridine was already discussed by Hückel, right? And so this is, now we're talking 30s of last century. Right? So this idea is nothing new. You also have what is known as computational alchemy, which is very common within force field calculations. So you vary the parameters in the force field to go from one composition to another, right? Within force fields. And what you then get, to get free energy differences by establishing, using numerical integration to calculate changes like this, right? Where you would get this free energy integral by sampling, and now this is a Stadtmach average, by sampling derivatives of your potential energy with respect to this lambda in your force field, right? So let me add this here. So there's a force field potential, Stadtmach average of a force field potential, right? And you go from 0 to 1. Now, famous or known scientists who have been working on this, Wilfried van Gunsteren, who was a professor at ETH, and his student Chris Austenbrink, who is a professor at the University in Vienna, Boku University, or also Bill Jorgensen. He's at Yale, Boku, ETH, and many others who exploit this, for instance, to estimate changes in free energies of ligand binding. You can imagine how this can be useful for the computational design of new drug candidates, right? So there is a long tradition of this in computational chemistry as well. Now, what I'd like to use for this course, though, is a specific paper I also mentioned already. It's by E. Wright Wilson, who published in the Journal of Chemical Physics in 1962 a paper called the four-dimensional electron density. And he basically wrote down the expression for the Hellmann-Feynman derivative in the nuclear charge. So he writes the energy as W, which is a common symbol also for the variational theory. So he writes that as dc and integral of your expectation layer. So this is your expectation layer. And so by virtue of Hellmann-Feynman, this is then this. And from this results for the electronic term, then you have your charge and this results the integral of rho is x, y, and z. X, y, and z. Divided by the distance to the atom, right? So this is the distance to atom, the atom with respect to which you're differentiating. And excuse me, this electron density, of course, depends on your nuclear charge. And so what he's saying then is that you can get the total energy for some nuclear charge by starting out with your nuclear charge at 0 plus the integral over lambda times your rho c over distance. Okay. And well, no, let's not call this lambda, let's call this z, and z goes from 0 to your final z. In this paper, you get this. So this is the electronic Hamiltonian. This is basically, as far as I know, the first time that really the nuclear charge has been included explicitly as a variable within the quantum mechanical picture without any approximation. Right? This is so in the Huckel theory, you still carry through all Huckel's approximations. So this idea of the nuclear charge being a variable is something that is well established in this sense, right? And so I hope you can agree that even for fractional nuclear charges, we can get, as shown by Wilson, a meaningful quantity. Right? So you can integrate over non-realistic paths, right? Non-realistic interpolations, and you can still, because also the energy is, of course, a conserved quantity, you can recover an actually useful property. Right? So this is important because, of course, for many practitioners in the field, this is an awkward thing to do. Right? This does not exist in nature. And so many scientists actually fall prey to this fallacy that just because you don't see something, that it's not necessarily true that it doesn't exist or it is not useful, right? So this of course is sometimes where one quite often one has to do some explaining there. Okay, in 2006 I wrote a paper as a postdoc on extending this idea towards a grand-canonical ensemble in terms of protons and electrons. So if you wish to have look at a more extensive discussion of this, you can look this up. This is called the molecular grand-canonical ensemble EFT, which I published together with Mark Tuckerman. In the Journal of Chemical Physics, 2006. So we noted down an energy functional in a proton distribution, so Z, and an electron distribution N. Proton, and we presume bosonic sort of classical protons, right, and fermionic electrons. So this thing is the universal functional plus which depends on the electron density, which implicitly also depends on the nuclear charge distribution, of course, plus the external potential term. No, I'm sorry, I changed now to the use of n, small n, for the electron density, which is also, I mean, this is typical for charge distributions. It's another common symbol. But it is the same as rho, as we used it previously in this course, right? So this is identical with rho. And, oh, sorry, of course, the external potential of R. And then we have a 1/2 nuclear repulsion term, right? Which is now within a continuous proton charge distribution. You can write it like this, where this potential is simply the Coulomb repulsion potential, but without any intranuclear repulsion, right? So this V tilde or V bar is simply the R prime, Z R prime, and we formally introduce an error function which switches this off at R approaching R prime. So you typically have a width and then R prime divided by distance to each other, right? So that's a modified nuclear repulsion term, right? So basically you have an electron-electron interaction term here. You have a proton-proton interaction term, and the external potential term with the electrons. Now we can build a variation, a functional. By extending this with Lagrange multipliers, which impose our particle conservation, right? So so we call these Lagrange multipliers mu E and mu N, right? And so let's call this variation a function of omega, and omega is our energy as usual. And now come your constraints, once for the electrons. And again, the electrons are global, right? So it's not spatially resolved. So you can simply impose that the electron density has to integrate to the number of electrons, right? And now for the protons, this is not as obvious because you don't want your protons just to go to one number, right? That would then be the single atom. Then you could only deal with single atoms and basically only study the periodic table. So instead, we want to conserve the atomic number, the nuclear charge at each nuclear site. Right? So that imposes a local Lagrange multiplier. So we have this, and our mu n must be spatially resolved then. And at your nuclear charge density at the position of the atom has to be the nuclear charge of atom I. And we basically have here a chronicle symbol that switches that on, right? So this is now, and I apologize for this, this is not number of atoms anymore. We used Ni previously for number of atoms, but this is the nuclear charge of atom I, or the atomic number. Okay. Now, this variation of functional, right? This is what we have to minimize. So obviously we look at its variation, and in particular with respect to n, with respect to electron density, and then you get an Euler equation for the electrons. So 0 equals, and n is a function, so there's a functional derivative, and only the energy depends on n, so we have dE dN, and the Lagrange multiplier, right? So you differentiate that bracket with respect to n, then you get a 1 for the integral over the electron density, and the number of electrons is just a constant, so it doesn't contribute. So only μe survives, and the third term does not depend on the electron distribution, right? And from this then follows that μe, we can identify μe, our Lagrange multiplier, as the variation of energy with respect to electron density, and you can show that this is equivalent to actually the change of the energy with respect to number of electrons. So if you it doesn't really matter the spatial resolution of, so this is a function of r, right? This spatial resolution does not matter. It's a constant because your energy, the electron density, is already giving the minimum in your energy. So no matter where you vary it, the response is going to be the same. And so this is a global constant, and this is, according to Janak, then is related to HOMO or LUMO, depending how you go. And so it's also interpreted as electronegativity. You should look at Koopman's theorem, right? So this is the chemical potential of your system with respect to electrons, right? So the grand-canonical potential, grand-canonical ensemble, that's of course the property you want to look at, or also the occupation number, according to Janak. So this is actually nothing new, right? So you didn't have to go to my paper to look at this. It's just for completeness, right? This variation of functional, this auxiliary variation of functional, gives you, with respect to electron distribution, gives you the same result as it was already discussed in the literature. So that is consistent with our extension, but now, of course, we want to also vary with respect to Z. Right? And also here, of course, you get an Euler equation, and 0 is the functional derivative omega with respect to Z. And then, of course, you have the energy with respect to your classical proton distribution. So that is a priori a spatial function. And now we have, you find that we need to, what survives this is mu n, but spatially resolved. So now we actually have a function in space, which is your dE dZ. And this, due to Hellman-Feynman theorem, as also shown by Wilson above, and as we discussed also already, is nothing else than this electrostatic potential, which uses now our modified external potential. So this is by Hermann Feynman. Right? You have the electrostatic potential with this modified error function, because of course you don't want your protons, you want the protons everywhere in the system. You want to see where the protons would go, but at the nucleus, right, you want to switch off the intranuclear diverging repulsion of your Coulomb potential. Right? So that's all that is, right? But this is of course a function of space, and classically this makes a lot of sense, right? That's the very definition of the electrostatic potential. It tells you where probe charge, what is the derivative of your energy with respect to probe charge, which comes along, right? So this is the modified electrostatic potential. And if you go towards its value at the nucleus, then we call this mu n at r equals ri, right? We call it, we define that to be the alchemical nuclear potential. Now, we can look at some further properties of this by considering total differential. But I note we are already 10:15, so I think we will stop here for today, and we'll continue next week along these lines. Are there any questions? That doesn't seem to be the case. Then I still wish you a good end of the week. And thank you for the attention. See you next week. Bye-bye.
Thanks. Bye.
Bye.
Thank you. See you next week.